So the chapter 9, so similar to the chapter 8, except we added some of the SPDF stuff, right? So similar. It's going to be pretty easy to do. The first page of answers was pretty straightforward. Things you're already good at, like if it's going in 2 directions, it's probably linear or bent. It's going in 5 electron domains, that's trigonal bipyramidal. 4 electron domains, that's tetrahedral. Iodine trichloride, you'd actually have to draw that. How many valence electrons does iodine have, Saloni? Very good, it has 7. 1, 2, 3, 4, 5, 6, 7. Trichloride, so it has 3 chlorines coming off of it. How many electron domains would that iodine have then? 1, 2, and then 3 bonds. So it'd have 5 total domains. So it's somewhere in the trigonal bipyramidal family. So it's one of these because it's trigonal bipyramidal, and then it's the T-shape of those ones, so it's the T-shaped one. That's the stuff we're not terribly good at, right? Because that was new last chapter, and you are going to see that on this next test next week. ZF4, XEF4, XE has 8. 1, 2, 3, 4, 5, 6, 7, 8, and there's 4 fluorines coming off of it. That's going in 1, 2, 3, 4, 5, 6 directions. So it's somewhere in that octahedral family. The others don't quite do that square planar. Some of them do linear, some do tetrahedral. And the thing that's nasty about a question like 5 is you might have to draw 3 of those to find the right answer. Agree with that? Like some of them, you could look at this one and go, that was tetrahedral. And do that like in your head and cross a couple of them off. But finding the square planar amongst there might be hard. I think there's one other one that's easy to cross off. Why is that one definitely not square planar? Only has 3. Square planar's got 4 directions and 2 extra pairs. So, the same idea again and again and again. Model shapes, model shapes, model shapes. Ooh, some angles. When you draw this one, you end up with the boron, 2 fluorines, and an extra pair of electrons. So it would be approximately kind of like a trigonal planar. It would actually be just a little bit less than 120. Be a little bit less than 120 because that extra pair of electrons would push the bond around. And 11, that is a tetrahedral one when you finally draw it. I think I said in class 109, but it was like 109 degrees and 28 minutes or something stupid. It's actually like 109.5 degrees, but you're not supposed to do fractions with degrees. You're supposed to, we don't ever do that because we're not that type of mathematicians or whatever. Again, draw it, and then you can figure out which one to pick. For this SO2, that's one of the harder ones to draw. You have double bonds to both oxygens and then an extra pair of electrons on the sulfur. So that's bonds in 3 directions. Which family is that? Which electron domain? It's bent in the trigonal planar family, right? And so if it's in the trigonal planar family, it's about 120 degrees. That extra pair of electrons pushes it just tinier than 120. Not specific, not saying is it 118.7 or 118.9. That's evil with a capital E and a lowercase l. So you pick the size of the other letters. 16 and 17. Ooh, finally, hybridization. How did we figure out hybridization? Trigonal bipyramidal, let's draw that. You've got the central atom, 1 up, 1 down, 1 bond, another bond, another bond. You've got bonds in 5 directions, or maybe you have bonds in 4 directions in 1 extra pair, or you've got 3 directions and 2 extra pair, or some combination for a total of 5 electron domain geometries. Game on. So with hybridization, this is going in 5 directions. It's going to use an s orbital, some of those p orbitals in 1 d orbital, an s, 3 p's, and a d, so it can have electrons that are all available to bond. They have to be spread out so they can bond, but these shapes don't actually hold together. They blend together, and since we're blending an s, 3 p's, and a d together, they decided to call it an sp3d hybrid orbital, because it kind of looks like all three merged into wah wah. And you talk on top of yourself, and you talk on top of yourself while you explain it. How many directions would SP2 be in? 3. How many directions would SP in? SP3? And we just said this was 5. SP3D2? 6. So you can add together 1 plus 3 plus 2, tells you how many directions. It's funny how, like, there was a point in life 10 years ago where I didn't teach AP chemistry, and this other AP chemistry teacher was teaching this one day. And I was like, oh, you just count the number of directions. You know which hybridization it is. And she was like, what are you talking about? The teacher. And I was like, well, if it's in 3 directions, it's SP2, because 1 plus 2 is 3. And she was like, oh, that's so much easier. I was like, how are you teaching it? And this whole conversation took place in front of the class, kind of like this discussion that I'm making right now. All right. I forgot I was recording. Hey, how's it going, everybody? You look good, Drew. Number 18, hybrid orbitals centralized in an SP2 electron. Why is the electron domain like floating? It's a superscript for some reason. SP2 is trigonal planar. What's the hybridization of carbon dioxide? You'd have to draw it. Carbon dioxide double bonded in both directions. How many directions is the carbon going in? 2. It's going there twice and there twice, but it's still only going in 2 directions. So that's SP. You kind of have to just draw them and figure out how many directions they're going in, but you have to be good at drawing them. You have to be good at drawing Lewis dot structures. The other part is easy. If you draw a Lewis dot structure wrong, though, the other part becomes impossible, right? Right? Julie knows what I'm talking about. Oh. So these are all, this one, I think that minus sign is supposed to be a superscript. I think it's arsenic, 6 fluorines, and a -1 charge, which means the arsenic, which usually only has 5, has an extra 1, so those 6 fluorines can attack it. So it's going in 6 directions. I think it was pretty obvious it was going in 6 directions, though, because there are 6 fluorines to start off with. So it's one of those octahedrals. It is octahedral, not one of those. 22 is definitely the easiest question there. In the SP3, how many S's and how many P's are being used? 1 and 3. Yeah, that's pretty simple. All right. Sigma and pi bonds. What is a sigma bond? A single bond between 2 elements. How you doing? What if you want to make a pi bond? That's the second bond, and it might be here. I don't have Hannah to play with, so you've got to do the handshake with me. So the pi bond can be above or below. The trick is you got to keep going and like look around. Hey, Johnny, how's it going? Oh, we missed. It's your fault. Totally your fault. The pi bond is the second bond. This one has a sigma, a sigma, a sigma. And since it's triple bonded, it has 2 pi's. It has 3 sigmas between the hydrogen, the carbon, and the hydrogen. And then 2 pi's because there's a double bond. That first bond between the 2 carbons is a sigma. The others are both pi's. This is the worst symbol for pi I've ever made. Here's the best symbol for pi. There you go. It's obviously pi, right? Cheese? Wedge of cheese. Brie. She says it looks like brie. What about this one? There's 2 sigmas, a sigma, 2 more sigmas. That's 2 plus 2 plus 1 plus 1, which is 6. And then there's a double bond and a double bond. That's 2 pi's. Those are just counting. Not too big a deal. Same thing with 27. That's a lot of counting. The answer's 12. I think 28 and 29 are both pretty easy also. You're just counting the number of pi bonds. That's 2 and 1. 31, counting the electron domain levels. A blank is not included. We don't worry about any core electrons when we're talking about electron domain geometries. We're just talking about what type of electrons. Not the core. We focus on the valence. Yeah, this is valence. shell electron pair repulsion. We ignore all the core electrons, just like I ignore my core. Okay. Got a chuckle. I'll take it. More drawing, figuring out the angles. More drawing, figuring out the angles. More drawing, figuring out the angles. Bond angles. Oh, 35 is not as fun because there's 4 different molecules, and you might have to draw them all. A bunch of them are Cl3s, so then you have to go like they all like this is 3, that's 3, that's 3, so you don't know which one to eliminate. This is the only one that ends up being trigonal planar, so it's 120. Bromate, that is a -1 charge. The minus is for some reason way too low. So the bromine would be in the middle. It has some coordinate covalent bonding going on. No one likes coordinate covalent bonding, especially Andrew Linsman. I'm sorry, did I say your name wrong, right? I don't know what it is. Okay. I probably shouldn't record his name, though, so I'm going to not say that. I can't go back and delete it now, either. So his name is Franklin Joseph Andrew. Br to the O to the O to the O. The Br ends up throwing electrons out to some of the oxygens, and there's like a coordinate covalent bond in a couple spots. This oxygen turned into a fish. Maybe I'll throw the extra 1 electron on that oxygen, and then this one gets double bonded to the bromine. 1, 2, 3, 4, 5, 6. Bromine starts off with 7, but one of them was thrown out here to this oxygen. I can't double bond to the bromine. If I try to double bond, I'll actually have too many electrons. Yes, go. Have a good time. Yes, you with the green shirt. Luck. Okay. 38, no big deal. 39, no big deal. Kind of skipping those, trying to get to the harder ones. Same thing with 40. Good luck, guys. Just go. See you later, Joseph. All right. Why is this one 120? The way it's drawn, it looks 180, doesn't it? It's been drawn very poorly. Look at the drawing. The carbon is going in 1, 2, 3 directions. So that's actually trigonal planar, which is why the angles would all be 120s. A lot of times the people do bad drawings just to kind of make it fit on the paper. In reality, that thing would be like a Rocky Mountain, because you have a bent, a trigonal planar, a tetrahedral, and a trigonal pyramid. And so it would have like angle, 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 and it would be really difficult to represent on paper. So they fake it, and they just draw it straight, and then they make you build a model in the real world. So, all right, I'm skipping these here. I think you would figure them all out without me explaining them. I hate 37. It's just a bad question. I asked Sparkles to rewrite it. She didn't. Sorry. So I've turned it red because I hate the question. It's just not a good question. So ignore that one. And all of the others are pretty easy too. They're like polar, non-polar. The only thing that's really irritating about 49 through 51 is you got to draw them all to figure out. Some of them you could probably draw in your head and not have to show any work for. But the others you have to. Let's see. Again, 52, you'd probably have to draw it in your head. That's what shape is A, do you think, without drawing it on paper? Trigonal planar, she wins the trigonal planar. What about Nf3? Trigonal pyramid. If3 is seesaw, or no, it's T-shaped. It's T-shaped. That one, trigonal pyramid again. I'm looking at Aaron now for backup. A little bit of respect there. And the BF3, I can't do that one in my head. BR's got 7. And I got 3 bonds coming off it. That's also a T-shaped. So, hey, that was a lie. Of these guys, which ones are polar? This one's not polar. SF6 would be octahedral. Is that the one we just watched? Did we watch the video on that? The guy's voice dropped. We watched it in your class, didn't we? The guy's drop voice. Strike that, reverse it. The guy's voice dropped. I said dropped voice. Just flipped the word. Yeah, that guy's voice dropped low. When I was in college... Pause. That intermission brought to you by sulfur hexafluoride. And this is a bunch more just geometries to polar, polar, nonpolar. You need to be good at polar, nonpolar stuff. This is their homework. A lot of the same thing. There wasn't much new in there. Just giving you a second to see the answers. Yeah, I'm not feeling anything other than you need to practice. SF4, sulfur's got 6. Oh, it's got 4. What shape is that? It's one of my favorite shapes. It's got no, there's not an extra pair. Not square planar. Seesaw. Yeah, it's seesaw. Seesaw is my fave because it's a seesaw. It's polar because it got that extra pair of electrons there. I know that question doesn't ask about that, but it's got an extra pair, so it's definitely polar. We've seen this like 5 times now in this homework, ZEF4. More double, triple, sigma, sigma, pi, 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 pi. And I think that's the end. No, one more. Lewis dot structures. What else could we say? Other than SP, this is SP hybridized, going in 2 directions. It's also got 2 pi bonds, right? It's 2 pi bonds, 2 sigma bonds. It's non-polar. You could ask a lot of questions about the same drawing. So you got to make sure your drawings are well done so that you can answer lots of questions about them. And that is the last one. And now I stop recording.